All right, good afternoon again, everybody. My name is Chris Abbots, if you weren't on when I welcomed everyone a couple minutes ago. It is 2 p.m. by my clock, so I'm going to go ahead and get started and see as other people trickle in. So as I said, my name is Chris Abbots. I'm the Business Development Manager for Energy and Sustainability at Nortec Humidity. I've been in this role for about a year and a half now, and before that I was a product manager here at Nortec. So basically what I aim to do is find ways to save energy in both humidification and cooling through the use of evaporative humidification products. One piece of question I have for everybody here today, I'm going to put out a poll, and I'd really like it if you could take a second and answer this. What I'd like to know is how much of the psychrometrics do we actually want to go through today? How deep into them? No matter what, I have to show a psych chart, so I hope that's not too bad for everybody. But I'm hoping to see how in-depth we want to see. So I'm just going to give that a minute as the votes flow in. So we're about 65% of people voted, getting there. Give it another 15 seconds. All right, I'm going to go ahead and close the poll, and I'll share the poll hopefully on my screen here, or you should be able to see it. So as you can see, a plurality of us are voting for an overview, and almost half of us were looking for a little bit more depth. And then there's 17% of us that would just like to see some of it. So of course it's all over the map. I'll do my best to keep it not too heavyweight on the psychrometrics. If you have specific questions about it, please write them down as we go, and I'll try and answer them at the end. Maybe that's the best way for me to handle that. So what will we touch on today? So the first thing we're all looking for is, what am I talking about? How can we actually save with evaporative humidification? How much are we talking? And where do those savings come from? The next thing I'll touch on is the preheat penalty myth, as I like to call it, which isn't fully a myth, but as any myth, it's got a kernel of truth to it. But we have to look at it in a little more depth so we understand. We'll also talk about the rules of thumb for effective cooling with evaporation, as well as how we can apply for rebates with evaporative cooling and humidification, mostly across North America, but it can apply elsewhere in the world as well. So let's talk about evaporative humidification first. So this will focus at first on the humidification side, and we'll look at the cooling side a little bit deeper into the presentation. So we'll look at the different ways we can humidify a building as a brief overview. So to start, I like to put this slide up almost as a look how many things we can do slide. There's quite a few options when it comes to humidification, but they typically break down to electric, boiler steam, gas-fired steam, or evaporative humidification. And we can remove the names of the products and the different styles there and end up just with the four main ones, and then evaporative can be split into compressed air, ultrasonic, and other evaporative technologies. And this sort of breaks it down in a way where we can see the different costs between each technology or each type of humidification. So back to the basics. Every pound of humidification put into the air requires about 1,000 BTUs. I think it's 1027 technically. So steam humidifiers are either using electricity or gas to boil that water and put it in the air, whereas evaporative humidifiers are drawing energy from the air already in order to humidify or cool. So when we talk about the actual costs, again, we're looking at sort of the electric steam, gas steam, pressure steam, and then the compressed air ultrasonic, and the rest of the evaporative technologies to use. Now these costs don't include preheat or reheat, so I have to always point that out. But the three on the end, the high pressure, the DL system, the evaporative media system, typically can be applied for rebates and typically get rebates back from utilities for electric reduction. And that can even be from compressed air or ultrasonic humidification. To simplify it a little bit, steam, you're looking at 600 to 800 watts per liter. We've gone metric here. 50 to 75 watts per liter for ultrasonic, 30 to 50 watts in compressed air, and 6 to 7 watts in high pressure. And that high pressure can go back to the DL or the evaporative media as well in terms of energy usage. We just had the lights flicker in my office, but I think we're okay. So, where does this land in a real-life situation? So this is annual humidification costs all in for a New York City building, fairly large, 22,000 square foot building, 40,000 CFM air handler. It's an air side economizer that only needs 20% minimum outside air. And you can see that if you were to keep that humidified with electric steam, you're charging yourself 4 times as much as gas steam, which is exponentially as much as an evaporative system. You can see the utility rates down at the bottom, and you can see all of my assumption. If you've got questions on how I got to this, hopefully I'm about to step by step show you what we're doing. Sorry, I'm fighting with the questions here. So I have a question of, could I repeat the relation between flow of water into space and BTU per hour? So if we go back to here, basically when we're humidifying, we have to put in, we measure in pounds per hour typically. And so 1 pound per hour would be 1,000 BTUs per hour to put water into the space, no matter where it's coming from, plus or minus efficiencies. I hope that answers the question. Generally, I'm going to leave questions to the end, but if I notice that it's a quick answer, I'll answer it right away. So from a very basic psychrometric overview, steam goes straight up on a psych chart, and evaporative humidification goes from the bottom right and up to the left. Not that any of you can see it, but I did the motion with my hand to show where that was going. In a little bit more depth, which I'll get into in a minute, a lot of people say, look at this line here, this blue line. If I'm cooling, I'm going to have to heat. I'm going to have to do extra heat. So now I'm going to get a little bit into the preheat energy myth, as I call it. And what I hear all the time, and I don't blame people because this is what I said when I first heard about this style of humidification and cooling, is if I'm humidifying with an evaporative humidifier, aren't I just transferring the energy from the humidifier to the airstream? Yes, but you don't necessarily have to apply any more energy to the airstream. And for every BTU I cool, don't I just need to reheat? Not necessarily. In design condition, yes, and I'll get into that in more detail as well. And then won't my air side economizer be half as useful because I'm taking all this extra energy out of the air? And that I get a really good answer to, I think. So this is looking at basically a design condition day in this New York City building. It's cold. It's 15 degrees Fahrenheit, 16 degrees Fahrenheit. At that point, we can basically assume there's no moisture in the air. So no matter what, we will be humidifying this day. And our return air is somewhere in the 72, 73 degrees. And we want to be at about 40% because 40% is the optimal level for humidification. So if we were doing this with a steam system, we would heat, well, first of all, we actually managed to meet mixed air temperature here at 55 degrees without doing any extra heat for a steam system. And then, of course, we boil water and put the water in the air, and away we go. We're at our set point for our air supply air temperature. However, if you're doing it with an evaporative technology, you have to preheat that air and then cool it back down again. So this is the preheat penalty, and there is absolutely a preheat penalty. And in design condition, you will need to preheat approximately equivalently to what you need to heat for a steam humidifier. However, the vast majority of the time, we're not in design conditions. So here's an example of when a evaporative humidification system can be extremely effective. This is a day, it's about 62 degrees outside, 61 degrees outside, and 50% humidity, probably around this time of year, actually. So your economizer's running, but in order to maintain your 40%, you need to humidify that air. But you also need to cool that air in order to maintain your 72 degrees in space. So what you do with the steam humidifier is you boil water and you put it into the air, and then after your air is humidified, you still have to cool it down, so you're still running your cooling coil. And all told, you put in 2.6-ish BTU per pound of dry air. Meanwhile, the evaporative humidifier, you get to just go straight from your outside air point, spray water in the air, and move and reach your set point for the air supply. So in this case, if we go back and forth here, we're using 100% outside air because our air side economizer is in full bore. We have to humidify it and we have to cool it. In the humidified by evaporation standpoint, we are putting in effectively zero energy. We are just using the evaporative humidifier to cool the air. We can look at some other situations here as well. This is a situation in which the energy put into a steam system is, again, you need to boil it. So you've mixed your air side economizer to about 55 degrees, which means you've pulled in around 16,000 CFM. The number's not that important. You've pulled in more outside air than if you're humidifying with an evaporative humidifier. With an evaporative humidifier, you actually mix to an enthalpy set point. And at that point, your outside air, your mixed air temperature is around 61 degrees, and you can just humidify evaporative, again, using zero energy, as opposed to the 1.8 BTUs per pound that a steam humidifier would have to put in. And finally, we've got one of these situations where the difference is basically negligible. The outside air is cool, but cooler than our set point, so we're able to mix to our set point. An evaporative humidifier is putting in effectively 0 BTUs per pound, whereas a steam humidifier is putting in 0.3 BTUs per pound to maintain your set point. I go back and forth on that a few times. So let's go back to our preheat myths. Aren't I just transferring where I apply the energy? Not necessarily. Again, if we go back to the design condition slide, in this case, yes, that is what you're doing. You are transferring where you apply your energy. But in the other 95% of the year that you're humidifying, you will find some energy savings by evaporative humidification over steam humidification. Whoop, overshooting. The other one is for every BTU I cool, I need to heat. Well, as I said, a lot of the air is recycled. So that was when we were going through the slide where I was looking at bringing in more outside air for a steam system than for a evaporative humidification system. So instead of adding heat, and this obviously affects the economizer question as well, but instead of adding heat, I'm just bringing in less outside air, where allowed and where appropriate. And then finally, what about my air side economizer? Well, in reality, we actually extend the amount of time an air side economizer can be used by providing a little bit of extra free cooling in here. Now in this building, and of course I did pick this building to be a absolutely amazing situation for evaporative cooling. However, it can be effective in a whole load range of other situations. In this building, this would have been approximately a 39% overall energy reduction. Heating, cooling, humidification, lighting, plug load. assuming this 20.7 kilowatt hour per foot squared average that I've used from the CBECS census is accurate. The savings that we can apply with this evaporative humidification over electric steam or gas steam is huge. Gas steam is less expensive than electric steam, but the amount of energy applied is the same. So let's get into evaporative cooling directly. What are the different ways of doing evaporative cooling? So not necessarily humidification, but just evaporative cooling. Rules of thumb, things to watch out for, and problems that you can find with evaporative cooling, and where we can apply evaporative cooling effectively. What regions, what buildings, etc. So, different methods. There's direct evaporative cooling, which is humidifying and cooling the air that is going into the building or is already in the building. So that would be in space or in duct. And then there is indirect evaporative cooling, where we apply the cooling to either exhaust air or outdoor air, or even cooling towers, which is approximately the same as applying to outdoor air, but I'll show you the difference in a moment here. Excuse me. So in space, so this is exactly as it sounds, direct evaporative cooling in space. In this situation, we have a high pressure system spraying water directly into the room. And inside this room, we're using the room temperature to reduce the air temperature. In the duct, it was fairly straightforward. This would be a classic humidification where we're putting in fresh air, preheating or pre-cooling, and running it through the evaporative humidifier to cool further. So typically, actually, you'd have, if you needed a heating coil, and a cooling coil would come after the humidifier. Generally, the humidifier can add, the goal in this situation would be to reduce the overall cooling needed, not to reduce peak load or anything like that. On the indirect side, we've got cooling the exhaust air from the building. So this is actually incredibly common, especially in Germany right now, but we're starting to see it in North America, where the fresh air is coming through ideally a sensible heat exchanger before being put into the supply air. And we're taking our conditioned return air and saturating it. So we're making as big a difference on the sensible temperature side, the dry bulb side, as possible, allowing us to cool the fresh air as much as possible. And then we can also cool outdoor air directly for a 100% recirculation unit. So the fresh air is coming in through a heat exchanger. What you're currently seeing is a typical fresh air cooler, but we can put a humidifier inside of this in order to allow for additional cooling of the fresh air. Finally, cooling towers, I'm not going to talk about very much, but it's very similar to what we were just looking at here, just they are remote. Typically, they're done a secondary heat exchanger and a chiller. Most of us are familiar with cooling towers, so I won't go into too much detail. Now, let's get into detail on the fun stuff. So in-space direct evaporative cooling is typically the highest potential for energy savings. Not peak load savings in most climates, but overall energy savings. Inside the room, we're limited by the room temperature. Obviously, we can't overcool, and that's typically not a problem. As well as room humidity limits. We don't want to put the truth to the word swamp cooling, which is not a term we typically use, mostly because we no longer consider any of this swamp cooling. We're not very swampy anymore. We have to watch cooling coil humidity limits, which I will touch on in a minute. And we also have to watch the amount of outdoor air. And that's because if we don't have enough outdoor air, we can't humidify. We end up over-humidifying the space. So we can only humidify the amount of outdoor air coming in. Now I've got this little cup here at a 25% RH at 72 degrees Fahrenheit. the reason the room temperature and room humidity limits is better for in-space direct evaporative cooling as opposed to induct evaporative cooling is because we have a lot more space to fill this cup, per se. If we look at induct evaporative cooling, where we're cooling and humidifying directly inside the air handler, then typically we've got a supply temperature of about 55 degrees, and this 46% RH is the exact same amount of water as this 72 degrees and 25% RH. So that's where we can see greater savings with the in-space direct evaporative cooling. Generally, we see in-space applied in factories and warehouses and places with larger ceiling heights, but we're seeing it more and more in even as low as 10 feet or 8-foot ceilings in smaller commercial type applications. So the induct evaporative cooling is limited by supply air temperature. Obviously, we can only fit so much water in 55 degrees, as well as the room humidity limits and the cooling coil humidity limits, as well as the amount of outdoor air. So a lot of the same problems, a lot of the same limitations, but one extra one where the supply air temperature is lower than the room temperature. If we look at indirect evaporative cooling, this is the exhaust air cooling. So once again, we've got the return air coming from the room, typically 72-35% or 74-50% in the middle of the summer, but that still allows a fair amount of humidity to be put into the return air to cool it down. We can see a 10 or 15 degree drop before putting it through a heat recovery unit. As a lot of us know, we tend to avoid using heat recovery units in the economizer season because we're just overheating the air. However, during the peak heating season or peak cooling season, we'll see energy savings here from the cooling side. We can also cool the outdoor air. So this is a 100% recirculation unit being cooled by the outdoor air through a sensible heat exchanger. If we cool that outdoor air as much as possible, again, we're seeing recovery of that cool air through the sensible heat exchanger. But we're limited by the outdoor air humidity, and we're limited by the outdoor air temperature. If the air is too cool, we can't do very much with it. And if the air is too humid, we can't humidify too far. We can actually combine those two technologies, where this is the exact same diagram as before, but we could actually put in a damper just before the humidifier after the return air to pull in outdoor air when it's more appropriate to use the outdoor air for cooling. That's not something we've seen applied very much yet. There is a filtration need, obviously, for that. There would be an additional pressure drop to discuss, but it is a method that could allow for a few extra kilowatt hours savings per year. So I'm just going to take a quick look through the questions here before I move on. That one I can answer at the end. There we go. So there was a good question that I should have answered earlier on the number of, or the annual cost based on how many hours or pounds. So that was during the, I'm going to skip back to it before I forget. So the pounds per hour, which I now realize I didn't actually put on this, was somewhere in the range of 550 pounds per hour, and it was a 24/7 system that allowed the humidity in space to creep up to around 50% for cooling and stayed at 40% for the gas steam and the electric steam systems. In New York City, for a 24/7 system that requires 40% year-round, I believe we're looking at around 3,300 or 3,400 hours a year of the humidifier operating at some percentage. Okay, I'm going to go back to where I was here. So, rules of thumb and things to look out for. I've kind of just slapped these on the screen, but we're always making sure we design the maximum humidity in the space to be below the wet bulb of the cooling coil. Basically, we don't want to humidify to the point where the cooling coil is just going to pull that water right out again. In that case, we're not saving any energy. We've just changed how we're pulling the energy out of the air, and we're wasting water. Pressure drop should really be considered in every induct evaporative humidification system, whether that's evaporative cooling in the exhaust air, or if it's evaporative humidification and cooling in the direct airstream. No matter what, pretty much all evaporative technologies have some pressure drop. We're not talking a lot, somewhere from 1/8 of an inch water column to an inch water column, depending on the technology, but it does need to be taken into account. As well as distributor power, so that's things like princess heads for the high pressure in space systems. When we're looking at rebates specifically, we need to look at all the power use, not just the power use for the pump, for example. If you're using an enthalpy wheel, a full energy wheel, and that energy wheel has a frost coil on it, so that's a preheat coil for the enthalpy wheel, the direct evaporative cooling can actually reduce the amount of overall heating. So there's two different ways of using an enthalpy wheel to avoid frosting. You can either reduce the amount of airflow over it by slowing down the wheel or bypass dampers, or you can preheat the outside air. And if we're preheating the outside air, obviously we're getting less cooling effect from that outdoor air. And when we add in the evaporative cooler, we can reduce the amount of heat we need to apply. If you're using an enthalpy wheel, again, the indirect exhaust cooling will add humidity back to the space. So that's just something to keep an eye out for. Evaporative cooling can be used with desiccant humidification as well. So that's if you have a desiccant dehumidifier to dehumidify the air stream coming in, the fresh air. And that can be through waste heat or through solar heat. And you can put an evaporative cooler after that to significantly increase the amount of cooling you'll see in the air. And yes, you have some heating from the desiccant coil, but you'll end up with far more cooling than you do see in the heating side. And finally, the higher your supply air and cooling coil temperatures are, the more effective we can be with an evaporative cooling in duct. So that would mean if you're able to apply 60-degree air with 58 wet bulb, you have more significant cooling applicability. And for all of these situations, right now there's very few tools publicly available that will calculate your in-depth energy analysis that will be acceptable for rebaters, for example. So if you are looking to get a rebate specifically on humidification or evaporative cooling products, it's worth reaching out to a Nortec representative or Nortec itself for an in-depth analysis. So where can we do this? I recognize most people's first thought is Phoenix, California, places that are dry and hot. And yes, those are absolutely the best areas for this. That being said, this will actually work and work cost effectively from climate zones 3 through climate zones 8 of ASHRAE's climate zone map, regardless of moist or dry situation. That being said, the cooler and drier it is, the higher the humidification load is typically, and we'll see more benefit there, or the hotter and drier it is. So that would be, again, yes, Phoenix, San Diego, potentially I've done analysis in Toronto and Minneapolis as well that comes up with quite significant energy savings compared to either mechanical cooling or mechanical cooling and steam humidification. However, if you're in the southern tip of Florida or somewhere near Miami, there's a lot less we can do with humidification. This slide effectively just repeats what I said. so I'll move on. On the rebate side of things, we have seen some successful rebates. So this job specifically was around $100,000 in the New York State area, and I've spoken with rebate partners. If you're not aware, most utilities don't do the rebates directly. They move towards allowing a third party to research the rebates and put them out for them. So that's in Minnesota, Vermont, Arizona, Ontario I've spoken with, and they're in the process of some jobs that should get rebates as well. And then generally the easiest case is for electric humidification replacement. If there's an electric humidifier in the building with a relatively high load or relatively large usage case, we'll be looking at a fairly easy case for rebate there. That being said, we can absolutely apply for rebates with evaporative cooling standalone products, or even replacing a compressed air system, because compressors are one of the things utilities like to target to get them off the grid. So in this job specifically, it was about 1,000 pounds an hour of humidity, and they were doing that before with electric humidification. It was 60,000 CFM outdoor air, and they replaced it with in-space humidification. So it was about $90,000 for this one, and this is not the only one we've done in the area. So the next question is, and I get this fairly often, especially at trade shows, is how does switching out your humidification compare to doing things like putting in solar energy? Because a big reason people do this is to save money, and what's the payback, etc. So if we look at this chart here, I'm not going to tell you where it is yet, but if you're going to put in a solar system, you've got this big blue bubble on the right, and it's big because you have to spend a fair number of dollars per kilowatt hour saved. So the bigger the bubble, the more dollars you spend for one annual kilowatt hour of savings. So you can see solar is quite large. If you have T8 light bulbs and drop down to LED light bulbs, it's a smaller bubble. If you're looking from T12 to LED light bulbs, it's an even smaller bubble. If you just recommission the building, that's one of the most cost-efficient ways of saving yourself energy per year. And just putting in lighting controls so that the building isn't lit up year-round 24/7 is another way, that very inexpensive way to save some money. Interestingly, switching out your electric humidification to a evaporative humidification system is more expensive than switching out your lighting, and it's more expensive than doing a recommissioning, but the size of the bubble is quite small, and that's a very positive thing. That means the number of dollars we spend to save thousands of kilowatt hours per year is very small comparatively. Now, I show people this, and people say, well, where is this? It's got to be Phoenix, right? It's got to be Las Vegas. This is actually where I'm from, Ottawa, Canada, where we can save that many kilowatt hours per year using an evaporative cooling system. Coming soon will be a case study on a building we did here that had their chiller shut off for 1 month in the fall and 1 month in the spring, that before they would have been in full cooling mode just by using evaporative humidification. So it can be quite effective, and it can be quite effective almost anywhere. But I do have to put up the Phoenix slide as well so that we can see the comparison. Phoenix actually has a lower humidification load, which is where a lot of the savings can come from. Despite being very dry, it's nowhere near as cold. That being said, the size of the bubble is still comparable to these recommissioning and putting in lighting controls, and less expensive per kilowatt hour than T8s, T12s, or solar. You will notice I shrunk the size of the solar significantly for Phoenix because they have much better sun than we do in Ottawa. I was in Phoenix recently, and I miss it already. So I went through that slightly faster than I was expecting to. So now I can take questions if you have them. If it's a quiet question period here, I will go back and start looking at the psychrometrics a little bit more in depth if there's interest, which I think there would be. So I'm just going to look at the questions here. We have one asking, where's the best location for the humidifier? Is it before or after the cooling coil? And what is the relation with the heating coil? So in an ideal world, our heating coil is before the humidifier and our cooling coil is after the humidifier. So I'm going to try to go to slide where I can maybe draw on the screen here. So if we look at this guy again, sorry, my computer's frozen up slightly. There we go. Ideally, we have our heating coil right here. That's not going to allow me to draw on the screen. I apologize for that. We have our heating coil here, right in front of the fresh air, or right after the fresh air intake, followed by the humidifier, followed by the cooling coil. And we like to see that, so if there is a preheat need, we can do so before we humidify the air. And if there is any excess water or the cooling coil doesn't have to kick in until it sees the temperatures getting too high after the humidifier, if that makes sense. We have a question about the quality of the water for evaporative humidification. So there's different evaporative humidifiers for high pressure and DL systems, the DL being the dual humidifier that uses a pressurized water and a media. Both of those require reverse osmosis or better water. For systems such as the media evaporative, the ME system, we can run that on potable water. Similar to how steam humidification works, generally the better the water quality, the less maintenance is going to be required. So generally RO or better is what we recommend, but with some systems, compressed air and media evaporative systems, we can use RO or potable water. I'm not seeing any other questions here right now, so I'm going to go back and touch on the psychometrics again. Please go ahead and ask at any time. I'll keep the questions open. And if we're looking, if anybody wants to float an idea for or float an actual situation that they're looking at, I'd be happy to take a quick look on a psych chart at that live as well. So in this situation, again, this is the basically design situation, design case situation, where we've got your coldest outside air and your return air is, again, it's around 71, 72 degrees. So if you're familiar with psych charts, you know that when you mix outdoor air or mix two air streams, the mixing point is somewhere along the straight line between the two. In this case, our minimum outside air happens to bring us pretty much to 55 degrees, just a little bit higher, actually. So in this case, when we reach that point, we've got an air that's approximately the right temperature because we're in heating mode, but we still need to add the humidification. Because we've mixed our 40% return air with our, yes, it's 90% RH outside air, but it's a very low water capacity down there. So we've mixed up and we've hit somewhere around 56 degrees and 52%. But in order to reach the return air or the room air set point, we need to add a few grains to that, a few grains per pound of dry air. A few thousand. And to do that, we have to boil the water. So when we boil the water, you can see we go straight up. So we don't affect the air temperature when we're boiling water with steam, or humidifying with steam, excuse me. And we end up at a point pretty much directly above our mixed air point. However, if we're using an evaporative system and we don't have any additional heat to use, waste heat, etc., then we will need to preheat in this situation. So we have effectively the same mixed air return air point because it is the minimum amount of outside air we can bring in, and we're in heating mode. So we have to heat that up in order to get to a point at which we can evaporate water in the air and land at 55 degrees, because that's our goal supply temperature here. So this would be done with a gas heating coil, hot water coil, or electric heat, typically. And as you heat that up, you end up somewhere around 61, 62 degrees in this specific instance. We can see preheat needs that bring it all the way to 72 degrees at design condition. But what we have to remember is we're not at design condition very often. And humidification and evaporative cooling is one of those pieces of technology that allows you to modulate down very, very well without losing efficiency. On the 100% outside air situation, where we're dealing with an air side economizer, what we're looking for here is basically we know we're bringing in 100% outside air. I don't know if I can get too much detail in this one, but we have to bring in 100% outside air because it's the coolest, least enthalpy, least energy available to us, and we need to cool our building. And we need some mechanical cooling in it. And like I said, I think I've gone over this one enough. So I've got a question here about the DL specifically. How is it controlled to utilize the most energy savings in a heat wheel custom air handler application? So if we're looking at the DL, it works the same as any of these other situations in which we have induct cooling. So we would be looking at an induct system like this. However, there'd also be, in this case, in the question, we're looking at a heat wheel as well. So rather than a sensible load, we'll be looking at, or a sensible heat exchanger, we'll be looking at an enthalpy wheel that transfers both humidification, or humidity and energy out of the system. So when we're looking at a DL, in this case, we would apply it for direct cooling and humidification. Depends on the amount of outside air we need, of course, but typically we'd control it with an enthalpy goal. So if I go back to, well, it's not the best slide. This is the best slide for this. If I go back to this, what we'll be aiming for is we'll put typically enthalpy sensors in the economizer system. So rather than controlling to mix to 55 degrees, we tell the sensor to mix to around 19 BTU per pound enthalpy or something like that. It's easily calculable, and it's typically the same for most buildings. So you end up around 19 or 20 BTU per pound coming in from the outside air and the economizer. When in economizer mode, you're typically skipping your energy wheel. So that's the situation we're looking at here, where instead of bringing in 100 or 60% outside air, we bring in 50% outside air or something like that in order to bring us back to our humidification set point and temperature set point without adding energy. When we're looking at a wheel, a wheel itself will typically be used either in the coldest season or in the hottest season. And in the hottest season, we're not going to be able to do very much to cool additionally because the air is typically so very humid in the first place. But in the middle of the cooling season, the heating season, the coldest time of year, when the enthalpy wheel is running and recovering humidity from the building exhaust stream, what we'll see then is a slight reduction in the load for the DL system, and the controls would be very similar to as if you were running a steam system, except we'd be looking to have that preheated air rather than just leaving it at 55 degrees. So there is some math to be done by the building management system to make sure the mixed air temperature is heated enough to cool back down to set point. Admittedly, enthalpy wheels do complicate things, but on the other hand, we're able to design around them and design to continue to use as little energy as possible. Yeah, did I cover that question there? Okay. So if we look one more time at this one, this is a situation where a lot of people have turned off their humidifiers at this point. It's getting warm outside, and it's humid outside. But that being said, you really shouldn't turn off your humidifier until you're beyond the point of the economizer season. Up until the end of economizer season, where you're still potentially using mechanical cooling, but there's enough outside air coming in that you may need to humidify as well. So that would be, for example, still this situation where it's economizer season. Your heating system is certainly off at this point, but you still do need the humidification. And this is a more extreme example of that, where you don't need a lot of humidification, but just a little bit of humidification to keep yourself at your set point. So, do we have any other questions, or are we looking for any more detail that I've missed? I can still see we've got quite a few people here, so I'd love to answer anything else. Okay. Well, in terms of energy savings, so at one point I put on the screen here, and let me see if I can find that slide. To say that it was approximately 39% of the energy savings overall in this building. And this was the, if you remember, the 22,000 square foot New York City building. Now I've seen that number range depending on the system. Just to give an idea, if we're doing cooling in space, I've seen that this is a 39-40% number. It can be pretty significant if you're humidifying anyway. If you're not humidifying and just looking for evaporative cooling, we're probably looking at depending on the area and how much heat's in the building, 5 to 15% of the cooling load can be removed by evaporative cooling. If we're doing an induct system compared to electric humidification, again, we're probably looking at a 20-25% of the electrical load being removed from the building. And of course, if we're looking at cooling only, that number is a little bit smaller, probably 5 to 10% for cooling only induct. Again, these are very ballpark numbers, but they're a starting point at least. So I've got a question. What would be my product of choice for energy savings? So as I said at one point in here, but it's a good question. I should make it a little clearer, I think. See if I can find the slide. Typically, your in-space evaporative cooling is going to be your greatest potential for energy savings, which means to do an in-space cooling, you are going to be using a high-pressure system, our ML system, for example, or you'll be using compressed air fog, or jet spray system. And again, the reason I prefer this is the amount of cooling we're able to do and be effective without over-humidifying is significantly more than in the other induct systems. That being said, if you have humidification problems, you're generally too humid, this would be my preferred system, and I'd actually do this with a media evaporative system, where we have the return air being humidified effectively to saturation and running through a sensible heat exchanger. And when it makes sense to do, which will be, again, a fair portion of the airside economizer season, we can open up an outdoor air damper to allow more outdoor into that return air feed and save even more on the kilowatt hour section. So it's a bit of a complicated question. When it comes to in-duct direct evaporative cooling, there is where I choose to use the DL system for its great hygiene, low water waste, and very low pressure drop as well. So basically, I'd use an evaporative humidifier in one situation or another. All of them have their advantages and disadvantages. Well, if there are no other questions, I can stick around for a minute or two, but I don't want to hold anybody on the webinar when I've got nothing else to say. I hope we've all learned something this afternoon, and if you haven't learned something, I hope you solidified some understanding of evaporative humidification and the real advantages behind evaporative cooling. We can see some fairly significant energy savings, and with rebates, we're talking 1 to 2 year payback periods in replacing a lot of electric humidification or even gas steam humidification. And when we look at evaporative cooling on its own, we're potentially using a less expensive system, which allows us again to see 1 to 3 year payback periods, depending on the setup and the location and the building economizer and how much fresh air. And I could go on. There's lots of depends. But that being said, there's always a good reason to look into it. So that'll be my end of my spiel today. And thank you all for attending. I believe this webinar was recorded. Yes, it was. And we'll be able to post it sometime in the near future for anybody who missed it or wants to show it to customers or colleagues. So have a good afternoon, and I wish you all the best on the weekend.